In this chapter, we will learn about the fundamental data preprocessing steps at LLMs. This preprocessing includes splitting text into word and subword tokens, and then converting tokens into vectors that fit into the model. The first step in preprocessing is named tokenization, where we split the input text into individual tokens, which are either words, subwords, characters, etc. As instance, consider the tokenization scheme we showed in this figure. In this tokenization scheme, we split text into individual words and punctuation characters. For this specific example, the sample text gets split into 10 individual tokens, as you can see here. The next step in preprocessing is converting tokens into token IDs. To map the generated tokens into token IDs, we have to use a vocabulary that contains all unique tokens in the training set and is usually stored alphabetically. As a simple instance, see this figure as shown here. The vocabulary defines how we map each unique word and a special character to a unique integer. In practice, we need to modify the tokenizer to handle unknown words. We also need to add some special context tokens. These special tokens can include, for example, markers for unknown words and document boundaries, for example. In our example, we modified the vocabulary by adding two new tokens, unknown and end of text, as illustrated in this figure. The unknown token represents new and unknown words that were not part of the training data and thus not part of the existing vocabulary. The end of text token can be used to separate two unrelated text sources. Now let's look at the tokenization mechanism in real-world LLMs. As an example, the GPT-2 uses a technique named BPE, byte pair encoding. The algorithm of BPE is shown here. It consists of two main steps. For using BPE, the entire training corpus, that's web text, as mentioned before, is first converted into a sequence of raw bytes using an encoding like, for example, UTF-8. Okay, in first step, the vocabulary is initialized with all 256 possible byte values plus one special token for end of text. In second step, that's iterative, the algorithm finds the most frequent adjacent pair of byte tokens by scanning the entire training corpus and merges that pair into a single new token. This step is repeated 50,000 times. For example, BP looks at the text and sees that the byte for letter T and the byte for letter H appear together constantly. So it creates uh, a new token that represents TH and adds it to the vocabulary. In another iteration, maybe the most frequent pair, maybe TH and E. So it merges them into a new token for the word T. Note that after 50,000 round of token merging, the final vocabulary size of 50,257 tokens will be established. Here is some notes regarding using BP for tokenization in GPT-2. First, the vocabulary is constructed before the pre-training of the model parameters. Two, there is no need for unknown token because every unseen character can still be broken into its underlying bytes. And three, if you let BPE run wild, it might merge things that do not make sense. To prevent rank merging, GPT-2 uses the following regular expression, regex, to pre-escalate text before merging. Okay, the last step in preparing the input text for LLM training is to convert the token IDs into embedding vectors as shown in this figure. First, let's review some backgrounds about embedding in machine learning. As we all know, machine learning models cannot process data formats like video, audio, and text in their raw form. Thus, we use an embedding model to transform this raw data into a dense vector representation that machine learning architectures can easily understand and process. Specifically, this figure illustrates the process of converting raw data like video, audio, and text into a three-dimensional numerical vector. When we are dealing with text embedding in LLMs, we should consider the semantic and syntactic information in mapping tokens to the vector representations. For visualization purposes, consider a simple two-dimensional word embedding where its scatter plot is shown here in this figure. When using word embedding techniques, words corresponding to similar concepts should appear close to each other in the embedding space. For instance, different types of birds appear closer to each other in the embedding space than in countries and cities. Now let's examine some word embedding techniques. The simplest form of word embedding is one-hot encoding. One-hot encoding represents words as binary vectors where only one position is one, making the representation sparse and non-semantic. So it's not suitable for LLMs. As a more sophisticated technique for embedding, here we demonstrate a simple version of the so-called word-to-vec technique. In this embedding method, to capture the semantic and syntactic information of the language, we use a fully connected neural network layer in which the input is one hot encoding vector, as described in previous slide, and its output is embedding vector of the token. So its input size is equal to the vocabulary size, and its output size is equal to the embedding vector size. Note that the embedding layer weights are trained simultaneously with all the other parameters during the pre-training phase. In fact, the embedding layer performs a lookup operation, retrieving the embedding vector corresponding to the token ID from the embedding layer's weight matrix. For instance, consider a small vocabulary of only 6 tokens, where each token is embedded in a vector of size 3, as shown in this figure. Here, the embedding vector of the token ID 5 is the 6th row of the embedding layer weight matrix. The embedding layer converts a token ID into the same vector representation regardless of where it is located in the input sequence. For example, as shown in this figure, the token ID 2 related to the word fax. Whether it's in the first or fourth position of the input token sequence will result in the same embedding vector. To inject additional position information into the LLM, we can use some sort of position-aware embeddings. In its simplest form, for each position in the input sequence, a unique position embedding is added to the token's embedding to convey its exact location. For instance, the first token will have a specific positional embedding, the second token, another distinct embedding, and so on, as illustrated in this figure. You can see here. As you can see, the positional vectors have the same dimensional as the original token embeddings. This is just an example. Okay, the summary of this chapter that was about input processing pipeline in the front end of the LLMs is depicted in this figure. At the first step, input text is first broken up into individual tokens, tokenization. Then these tokens are converted into token IDs using vocabulary. And finally, the token IDs are converted into embedding vectors to which positional embeddings of a similar size are added, resulting in input embeddings that are used as input for the main LLM layer. In next chapter, we will learn about attention mechanism in LLMs. That chapter explains about the reasons for using attention mechanism, about the causal self-attention mechanism, and about stacking multiple attention modules into a single multi-head attention unit. Okay? If you haven't done so yet, please join our community by hitting subscribe and the notification bell so you're always the first to know. Thank you for your attention.